All right, hi everyone. Here we have subtopic 3 here in illumination of the workplace. We've talked about 4 major quantities that we end up calculating quite a bit in this topic. Luminous, actually, let's go to the next one here. This can do it for us. Luminous flux, that is the total energy emitted from a light source in all directions. Luminous intensity, this is the luminous flux, the lumens of luminous flux energy in one particular direction, one steradian, or per steradian, how much energy goes in a direction. How much of that energy strikes the that's luminous intensity, I. How much of that energy strikes the object we're interested in, and that is the illuminance. Now we're talking about stage 4 here, luminance and reflectance. Okay, so illuminance is how much light strikes. Some of that light is absorbed, some of it is reflected, and this is the luminance L. Finally, we got one of these L words, and we're going to start with an L. That is going to give us essentially the level of light energy we need to think about, is our retina getting enough energy to activate things, rods and cones, right? Okay, good. All right. So here we go. I've said this, but now you can see it written. So light strikes the surface. Let's call it this sign right here, let's say. Some of the light is absorbed. I actually didn't say the whole thing here. Some of the light is absorbed. Some of the light actually passes straight through it. If you think about like a metal sign, very, very little of it, but you know, anytime light strikes something, some of that light passes through, is transmitted through, and some of it is reflected. Now, I have to add transmitted here too, because we use the same concept of luminance to talk about light that reflected off of something and then gets to the retina, and light that is projected into the retina, like from a luminous display, like what you're looking at right now. So, you know, the computer monitor that you're viewing, or the TV that you're viewing, is emitting light directly, well, not directly, but through a transparent surface, the screen on the exterior, and any material between the illuminating, you know, the illuminating element and its containers, then that passes through to get to your eye. So we can talk about the transmittability of a surface as much as we can talk about the reflectiveness of a surface. Okay. So again, these absorbed, reflected, and transmitted. So when we say luminance, we're interested in the what's available for the retina, as in what's reflected off and I can see, or what transmits through and I can see. And when we say, oh, that looks bright, what we're describing is the luminance of the light. The lights are essentially the luminance that is reaching our retina here, the observed brightness. All right, there we go. All right, now we have a photometer. I gave you several examples in 3.2 of me trying to use my photometer around my office. Photometers measure illuminance, right? How much energy strikes the surface. There is a device that measures luminance, as in, hey, how much light is coming in here directly? And why is that interesting? Actually, they're very expensive. And now Texas A&M Transportation Institute has at least one, or probably several of them, because they do research like this, which is, if somebody is driving and hopefully they're paying attention, but maybe they're not, maybe they're texting, and it's dark or whatever, and we have headlamps that we can, you know, we know the luminous output, the luminous intensity coming from headlamps. That light is then striking a sign, and maybe we want to investigate something like, what is the reflectivity of that sign? What if we put a certain coating on it that will make the reflection, you know, more effective? If we can reflect more of the light as opposed to absorbing more of it, we reflect more of the light, making the sign more visible. So, yep, headlamps strikes there. How much light off of the sign is reaching that human retina? And then we can ask ourselves, well, we actually, you know, we know things like from when we talked about dark adapted vision, there are levels of intensity in the light that we need to even activate our rods or cones. And actually our rods activate in lower states, right? And our cones need higher levels of luminance. And then we can start to study this and we can say, well, just to be able to see it at all, how much reflectivity do we need on this sign given a certain luminous intensity standard from, you know, from a headlamp, and given a certain distance away from this sign. So, and then, yeah, we can also study, well, how much do we need to be salient enough to capture attention, to attract attention when it's something that, you know, like a stop sign that probably should warrant capturing attention. There it is. That's our luminance gun. And again, this is telling us, you know, what is, it's not like with a photometer, it's how much light is striking this surface right now. This is the light that is almost like a beam, like you're pointing this thing like it's an eye, like it's a human eye, and that is the light that's available. All right. So luminance, finally we get our L. Oh, I forgot. There we go. Okay, so finally we get our L. We've got some mathematical expressions for it, but first, to understand what it is the light energy that is reflected or transmitted. So I always think of it like it's the energy that is available for the retina. It's the light that's done all the things it's going to do, and now it's gotten to the retina, and we're measuring it there. Okay, so how much light energy is there? And this is so this does not depend on an observer or how well I see or anything like that, or the viewing angle. It is only about the distance from the object that is the reflected or transmitted source, or surface, I should say. All right, now units, just like we had for everything else. So the units are called foot Lamberts. You recognize Lambert from Lambert's law. Okay, 1 foot Lambert is mathematically equivalent to 1 lumen per foot squared. Oh yeah. Okay, so where have we seen lumens per foot squared before? We've seen it before, and it wasn't called a foot Lambert before. Okay, so if you're confused, if you don't know what I'm talking about, recall the units. Go back to 3.1 if you have to, but you can also get this in 3.2. Recall the units for luminous intensity, lumens per steradian. For illuminance are foot candles, as we would refer to them, or lux, right? And mathematically, a foot candle is equivalent to a lumen per foot squared. A foot Lambert is equivalent to a lumen per foot squared. What? All right, so here is an important distinction. Yes, they are mathematically equivalent, but if you think about it, it kind of makes sense. We've got energy going in and striking something, and then we've got energy going out. And that energy can be expressed in the same units here, because it also, when that light is reflected off, it's still, in a sense, propagating, right? It's still on its journey from its original source, you know, until it gets to the retina. I guess that's its end place, and then the beam of light decides to destroy itself, I guess. But in any case, yes, they are mathematically equivalent. Do not get the 2 foot candle and foot Lambert mixed up, though, because that's the key distinction that tells me, are you talking about illuminance, how much light strikes the thing, or are you talking about luminance, how much light is reflected off and is therefore available for the human retina? Okay, the light that strikes the thing is not the light that's available for the human retina. Okay, so you do need to make sure you express, I'm talking about luminance, I need to see foot Lamberts as the final unit. And if we're talking about illuminance with an E, that's got to have foot candles, or lux are going to be your units there. Now, when you're doing all your conversions and everything, though, yeah, you can remember lumens per foot squared. It's mathematically equivalent. Okay, now, just like we did before, you know, with a, what am I doing with this? I don't know what candela per me. This should be, well, anyway, the conversion with meters and feet is the same as you would do between foot candles and lux. I think I put I don't know why I put CD there. Sorry about that. This is a lumens per meter squared, I suppose. And so, oh yeah. Oh, no. This is why I put it there. Sorry. If you go into the world of, I guess, like photography and optics and you know, going into a little bit more of the physics of light, there's another unit that's called a nit. This gets used a lot in photography, I guess. So I know some of the, you know, probably some of you out there watching this are photographers. You can probably fill me in on that. But there is a conversion there. If you ever see the term nit, it's like a hogshead, or like, you know, it's one of these industry terms, I suppose. But this is the conversion that you can do for it. In this class, I'm only going to be talking about foot Lamberts, because I really like to confuse people with foot candles. Foot Lamberts are the luminance. Foot candles are the illuminance. Good. Okay. I hope you got that. Matt, yeah. Okay. You got to specify it. There you go. Okay. All right. So I've already, you know, brought up that distinction. Luminance can be reflected off of a surface, or it can be transmitted through. All of these are examples of what we call luminous displays. And so, you know, the light is, again, projected from these. There are light elements behind those nice, you know, protective surfaces, and then the light transmits through. So we can use the same equations, or we can use the same way of referring to that light, because again, this is the light that is available to the retina. All right, here we go. So here's our math. So we have these constants, and these are values between 0 and 1. They have no units, which works out pretty nice mathematically when you're comparing things like foot candles and foot Lamberts, and you're thinking, how do I get from one to the other? Well, if you've got a nice unitless multiplier, and you can then recognize that mathematically we're talking about lumens per foot squared in each case, that's how it works out. All right, so our two constants, or our two two constants, reflectance and transmittance. Every surface can be characterized by both a reflectance constant and a transmittance constant. Generally, we're only interested in one or the other, because we're either talking about how much is transmitted from a display like this. There is a reflective property of the plastic or the polycarbonate coating on the surface of this monitor. There is a reflective property that is reflecting the light back into the, you know, into the computer or the display elements. But we're usually not interested in that. We're interested in with how much light gets through, right? Transmittance. So again, it's between 0 and 1, and it's essentially, think of it like a percentile, right? So how much is absorbed versus how much is reflected, how much is absorbed versus how much is transmitted. So here we go. So if you have a reflectance of 0, and you say, like, I've got a deep black painted wall, or like, what do they call it? Vanta black. If you have looked that up, VANTA black, it's like ultra black. It's the blackest. So in a way, it absorbs the most light in that sense. It reflects the least light. So yeah, you're in a room with a light source, a black wall looks black because it absorbs a lot of light, you know? And so, you know, the deeper that darkness is, essentially the less reflectance there is. If it is a mirror finish and all of the light, 100% of it is reflected, then it's an R of 1. Similarly, our transmittance constant here. Now notice this is, you know, it's a little bit different. It's a little bit opposite, but if you have a transmittance of 0, it's like it lets no light through. So it's like it absorbs all the light. And so then, you know, this would be an example of, you know, opaque windows versus clear. You can rate them based on transmittance, you know, shower curtain there. Flawless clear glass, you know, you would have 100% of the light transmitted through. So we'll find out these sorts of constants, and a lot of times you can characterize materials by their reflectance or transmittance constants. There we go. Don't forget those units, very key. And again, look, they are mathematically equivalent, so that's how these equations work out. but on one side, you got to make sure you call it foot Lambert, and on the E illuminance, those are foot candles. So yeah, I hope that's clear. I know we're talking about we're using two different words in order to basically specify essentially where in the path of this light beam are we interested. So this is the foot candle versus foot Lambert just basically specifies, are we talking about light that strikes the surface, or that encounters it, how much energy is there, or are we talking about the light that is in the free world ready for our retina to pick up? So here are some kind of common values you might see. I wonder if you buy a can of paint, if this would be the kind of thing that would be, I doubt it, but in any case, there are some of these, paint standards out there I'm sure you can find. So, white paint, it's not perfect, but it does reflect quite a bit of light. So if you look around the room you're in right now, my room, this room right here, right now, we use relatively white colored, very light colored paints. Another purpose for that is it helps illuminate the space. So if you can imagine, if I had in this room black painted walls, it would have a much deeper, darker look to it. And I'd have the exact same light source, right? So it does matter, the reflectance of the space in addition to the light source. So yes, white paint, very reflective. Aluminum, it's shiny, it reflects quite a bit. Going all the way down to black paint, it absorbs most of the, of the light. And I've got this interesting observation right here. And look at your own surroundings and look up and see what color the ceiling is, and look down and see what color, well, not color, what the surface of your flooring is like. And almost certainly your ceiling is a light color. It's a whiter one, because in general, we almost always want light to be reflected from our ceiling. We almost always have a ceiling over a place where we want visibility. And one of the easiest ways to do that, is to have a light colored ceiling. It's going to reflect the most light, of any of the painted surfaces, for example. But then why do we want, and at least in this room and other rooms, why do we want a darker color on the ground? And maybe you think about this a little bit, but in general, if you think about how we operate visually in any space we're in, think about if I want to see something, and that importance with, if you go back to 2.6, when we talk about contrast and the importance of distinguishing foreground and background. Well, almost always, if I'm trying to look at something, I would call that the foreground, and I'd call everything else the background. So I'm looking at this thing here, right? And generally, I'm not holding it up in the air and looking with the ceiling as my backdrop. My general posture is usually forward and down. So if you're in a space where you're looking at things, it basically is saying that, hey, if we have less reflected light coming from the ground up, we have effectively the light from top down that's usually behind us and guiding our sight is going to give us a much, the contrast of the thing we're looking at versus the darker background is going to really help our visual processing. So subtle human factors, creeping into architecture and aesthetic design of workplaces here. Okay. A deep mahogany desk, that's a good idea too. You got a nice white, piece of paper on top, very visible against that deep, dark background. All right, good. So we have some reflectance standards. So you can find these, this is a published standard then that would go into, like industrial facilities, to have a safe workplace with regard to the level of visibility you need. So the ceiling must be reflective. The walls should have this much reflection. And again, like we said, the floors should be minimally reflective, I guess. So these are always the, essentially the floor ends up being the darkest or the least reflective surface usually in any human space. Good, I already answered that question, guys. So there it is. Okay. All right, that's 3.3. One more section, 3.4. Thanks, everyone.